Hello, physical science students, and welcome to our video about wave properties. We're going to look at the parts of transverse waves and the parts of longitudinal waves, and be able to name those. We're going to look at some different properties of waves, wavelengths, frequency, period, amplitude, and how we calculate wave speed. So what are the parts of a transverse wave? Well, we have crests and we have troughs. Pretty obvious, right? The crest is the peak and the trough is the low spot. We also have the wavelength as being the point between troughs or the point between crests. Essentially, a wavelength is the distance between a point on the wave and the nearest point that is exactly like it. So that's why we oftentimes say at the point between troughs or the distance from crest to crest, because it's easy to tell this point is exactly like this point. And this point is the nearest one exactly like this point. That's an easy way to measure the wavelength on a transverse wave. Now let's look at what longitudinal waves look like and what are the different parts called of a longitudinal wave. We have the area that is called the compression area. It's the more dense region of the longitudinal wave. And then there is the less dense region called the rarefaction. Since the wavelength is the distance from one point on a wave to the next point exactly like it, you can see how we could look at wavelength being this long here on a longitudinal wave. If you could find out the point here to the point here, that could be a wavelength. This is pretty easy. Right in the middle of that compression area to the very center of the next compression area is a pretty easy way to measure wavelength on a longitudinal wave. So let's review our ideas here. Wavelength is oftentimes represented by lambda. It's a Greek letter, and it looks like this, lambda. It is the distance between one point on a wave and the nearest point, just like it. Now let's introduce another property of waves, and that is the frequency. You can find frequency represented by a cursive lowercase f. That denotes frequency. There's another Greek letter, nu. It kind of looks like a cursive V. Sometimes it's represented that way. In this class, we'll represent it with a lowercase cursive f. Frequency is another property that basically means the number of wavelengths that pass a fixed point each second. Another way to remember it is how frequently do the waves go past that point. And it would be some number per second. It's measured in inverse seconds. When we have a high frequency, we have a lot of waves going past a certain point per second. A lower frequency would have fewer waves going past that point per second. Frequency and wavelength are what we call inversely proportional. When we have high frequency, we will have a short wavelength. You can see the wavelength here is shorter than the wavelength here. If we have a longer wavelength, we will have a lower frequency. So we call those inversely proportional. The period of a wave is another property. It is the amount of time it takes one single wavelength to pass a particular point. So the period would simply be how long does it take for the wave to travel this distance. Now let's take a look at the relationship between frequency, wavelength, and wave speed. So when we talk about the speed of a wave, here's the V for velocity, the velocity of the wave, the speed of the wave. The speed of the wave is equal to the frequency times the wavelength. And if you think about this, you can recall that frequency and wavelength are inversely proportional. That means if I have a particular wave speed here, okay, and I have some frequency and some wavelength, and I can tweak those, if I increase the frequency for that speed, the wavelength will be decreased. If I increase the wavelength, the frequency will be decreased in order to maintain that particular wave speed. That's how these are inversely proportional. We always measure the speed in meters per second for waves. We measure the frequency in per seconds, which is the same as hertz. Hz stands for hertz. And we measure our wavelength in meters. So the speed of waves has a lot to do with the wave itself, but also the medium through which it is traveling. Sound waves actually usually travel faster in liquids and solids than they do in gases. They also generally travel faster in a material if the temperature of the material is higher. Light travels more slowly in liquids and solids than light would travel in a gas or in a vacuum. So it depends a little bit on the wave and on how that interacts with the medium through which it's traveling. So let's do a little problem here, an example. What is the speed of a sound wave that has a wavelength of 2.00 meters and a frequency of 170.5 hertz? Well, let's write our formula down. We know that speed equals frequency times wavelength. Now let's fill in the numbers that we know. We know that the wavelength is 2.00 meters. So we can substitute that in, 2.00 meters for our wavelength right there. Let's see, we know the frequency is 170.5 hertz. So 170.5 hertz. That's our frequency. Now we can calculate the speed. The speed equals those two multiplied together. 341 meters per second. If you'll recall, hertz is the same, basically a hertz is just a second to the -1, or 1 over s. It's an inverse second. It's a per second unit. So when we look at our units here, we know we have meters per second. And that is how fast this sound wave is traveling. So let's look at another property of waves. This is the very last one we're going to mention. It's called amplitude. Amplitude is a measure of the size of disturbance from that wave. If the wave's amplitude is greater, the disturbance from that wave is greater. Amplitude is also measured differently for longitudinal and transverse waves. So let's first look at longitudinal waves. When we think about higher amplitude, more disturbance, that means that in the compression part, and these represent the compressions and these the rarefactions here. If we're talking about greater amplitude, that'd be this one, we are talking about the coils in the compression being even closer together and the coils in the rarefactions being even further apart. When we're talking about lower amplitude, we are looking at relative to each other, relative to a higher amplitude. In lower amplitude, the coils in the compressions are not quite as close. They're a little bit farther apart than when I have less amplitude. And then also, the coils are a little closer together in the rarefactions. So you would see more of an even distribution between the compression and the rarefaction. As opposed to higher amplitude, you see much more dynamic difference between the two. And you could kind of think of that as, if we look from a side view of the slinky, lower amplitude would have the compressions be a little further away from each other and the rarefactions be a little closer together, so we're getting a little more even distribution, as opposed to a higher amplitude where these are really packed tight together and these are really pulled and stretched far apart. When we look at measuring amplitude in transverse waves, we're looking at the size of the disturbance, and we are looking at basically the height from rest position to the crest or to the trough of the wave. If A represents our amplitude right there, amplitude is basically measured as how tall is that crest, or how low does that trough go from the rest position, from that middle line. You could also look at amplitude as being 1/2 the distance from the crest all the way down to the trough. And just keep in mind, amplitude of a wave is related to the energy that it transports. If the amplitude is lower, there's a lower amount of energy being transported. And when we have higher amplitude, this distance being greater, we have more energy being transported. So quick review. Know the different parts of longitudinal and transverse waves. How are wavelength and period related? What's the relationship between frequency and wavelength? And how do you calculate the speed of a wave? What is amplitude, and how is that measured in transverse and in longitudinal waves? Here's a little advanced idea. Please feel free to come up with your own ideas if you've got some different questions. I look forward to seeing what you have in class.